Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Homework Lesson 107. Problem number 1. In homework from lecture 102, problem number 4, you were asked to consider the Bohr model of a hydrogen atom. How fast does a ground state electron orbit the nucleus? Assume the ground state orbital radius is 5.29 times 10 to the minus 11 meters. Also, the mass of an electron is about 9.1 times 10 to the minus 31 kilograms. So, what are we asked to do here? We're just trying to get an idea about how fast electrons move. And in this problem, we're going to basically equate the electrostatic attraction of the electron to the atom with the centripetal force. So what is the electrostatic attraction? Well, that's just Coulomb's constant times the charge squared divided by the radius squared. And that is going to be equal to the centripetal force, which is just the mass of the electron times v squared over r. And now it's just a simple matter of solving for r. And if we solve for r, we'll get that solving for the velocity. The velocity then is equal to the square root of the Coulomb constant times e squared, that's the charge squared, divided by the radius of the orbit times the mass of the electron. And then plugging these values in, what do we get? Coulomb's constant is 9 times 10 to the 9 Newton meters squared per Coulomb squared. I'm not going to write the units in. Times the charge squared, well, that's going to be 1.6 times 10 to the minus 19 coulombs squared, all divided by 5.29 times 10 to the minus 11 meters. That was the orbital radius that I gave you. And 9.1 times 10 to the minus 31 kilograms. That's the mass of the electron. And when we plug that in, what do we get for the velocity? We get 2.2 times 10 to the 6 meters per second. All right, problem number 2. Does running in the rain get you wetter? This is something I hear people talk about all the time. And I don't know if I got the answer right here. Your answer may be better. But the way that I'm going to set this up, I'll assume the density of raindrops, rho, is constant, as is the current density, J, which is just the current I, divided by A, the cross-sectional area, which is equal to rho, that's the density of raindrops, times the velocity with which they fall. So J is in drops per second per square meter. I is in drops per second. V is a constant speed of the raindrop in meters per second, which kind of makes sense because you might imagine if they're falling, they reach terminal velocity, and so they're coming down with a constant speed. And it says, hint, first consider the stationary state where your velocity u is 0. That's the velocity of the person. And then for the moving state, we'll let the rain move towards you instead of you moving towards the rain. So we'll give it the transverse velocity component that you otherwise would have ascribed to yourself moving through the rain. All right, let's see. This is the way that I would tackle the problem. First, let me just write down some orientation stuff here. If we call this maybe the y direction, and make this the x direction, and making this the z direction. And so you can imagine that a person will describe a person by a box, a rectangle basically, where here we have the area on your side, and then up here we have the area at the top. And so the number of raindrops that's hitting the person in the stationary condition is just going to be equal to the number that's hitting you in the top, on your head, plus the number of raindrops hitting you from the side. I'm really only considering this front side, since we're going to end up moving in this direction, and so the rain will be hitting us in the front. But we can rewrite this as simply the current times A sub t, that's the cross-sectional area on the top of your head, times some delta t, plus, that's for the top, and then basically the same thing, J dotted with A sub s, that's the cross-sectional area in your front and on the side, times the same delta t. And this will be equal to the raindrop density rho times the velocity of the raindrops v times a sub t times delta t. And this component here is 0, right? Because if it's coming straight down, nothing's going to hit us in the side. And so this will be, well, that is the expression for the number of raindrops that are hitting us. All right, so that's the stationary state. Stationary. Now what about if we're moving? Well, if we're going to move, what we're going to do, instead of having ourselves move, is we're going to have the raindrops move. And so I'm going to exaggerate greatly here the direction, the velocity direction of the raindrops. So we'll still have this component in the vertical direction of magnitude v, and then we'll have a velocity in the minus u direction, where u is the speed of, that's how fast you're walking, right? So we're walking this way, but if I put that relative velocity into the raindrop, then it's as if the raindrop is coming at me this way. And then the magnitude of this, of course, is just going to be, through Pythagoras, u squared plus v squared. That means, though, we can write v as the square root of u squared plus v squared times the cosine of theta, where theta is this angle here. And u we can write as the magnitude times the sine of theta. So now let's write the number of drops hitting us in the moving state, and that will be equal to the number that hit us on the top plus the number that hit us on the side. But now these values will be a little bit different. They're still going to be the current J times the cross-sectional area on the top of our head times delta t plus J times the cross-sectional area on the side times delta t. But this will now be rho times the square root of u squared plus v squared times the cosine of theta times a sub t delta t plus rho square root of u squared plus v squared sine theta times a sub s delta t. And I can factor out this common term here. That's rho square root of u squared plus v squared times a sub t cosine theta plus a sub s sine theta. And if I take the ratio of the number that hit us when we're moving to the number that hit us when we're stationary, that's basically dividing this term by this term, then we get 1 plus u squared over v squared times the cosine of theta plus the ratio a sub s over a sub t times the sine of theta. And you can see this is always greater than 1, which seems to me to suggest that you're always going to get hit with more raindrops when you're moving with some velocity in the rain. If you disagree, then feel free to post your own solution in the comment section. Again, I only thought about this for about 15 minutes, and I thought of it because it reminded me a little bit of the drift velocity problem. I was thinking about the drift velocity and how best to present that for the lecture, and it made me think of this raindrop problem that I'd heard many people talk about over the years. And so this is kind of my approach to it. And of course, if you stand still in the rain and you don't move at all, you're going to get much, much wetter. So, if you're out in the rain, don't stand still expecting to get less wet because you saw this video, because you'll be in the rain till the rain stops. If that's the case, you have to move to get out of it. So, but whether you should run or walk slowly, my guess is from the analysis I've done here, it tells you to walk at a slow pace, but as opposed to running. But I don't know. Maybe that's a different dimension of the problem that you could put into it and explore. Problem number 3, calculate the resistance R for a 12 gauge, 1 meter long wire of nichrome, whose resistivity at 20 degrees Celsius is 100 times 10 to the minus 8 ohm meters. And then part B, what voltage drop would you get across 1 meter of 12 gauge nichrome wire carrying 1 amp of current? Pretty straightforward problem. So part A, First thing we need to do is consider the area, the cross-sectional area of this wire. That's, of course, pi r squared if it's a circular wire. And this is going to be, since the 12-gauge wire has a radius of about a millimeter, this is basically going to be pi times 10 to the minus 6, because minus 3 squared is minus 6 meters squared. Then the resistance, R in ohms, is going to be the resistivity of nichrome, which we were given in the problem, times the length of the wire divided by the cross-sectional area. And that's 100 times 10 to the minus 8 ohm meters, times 1 meter, which is the 1 meter length of wire, divided by this pi times 10 to the minus 6 meters squared. And if we punch that into the calculator, we should get something on the order of 0.318 ohms. Okay, and then for part B of the problem, we're just going to put to practice Ohm's law, V equals IR. And we're told that we're going to use a 1 amp current, and so that's 1 amp times the 0.318 ohms, and we'll get 0.318 volts, which is a lot more than what we got across a copper wire, but that's because the resistivity of nichrome is pretty high. I used to use nichrome to create igniters to deploy parachutes in my model rockets when I was younger, because they can heat up, they can run a bunch of voltage to them, they get hot, and they'll ignite black powder, and so that's my familiarity with nichrome. Problem number 4, we're asked to show that this equation for the velocity is a solution to the differential equation that we talked about in class. And so that's pretty straightforward. If you know calculus, then this shouldn't be very difficult. Number 4. So first thing let's do is let's differentiate with respect to time this expression for the velocity. And that's going to give us minus q over this gamma times e times minus gamma over m times e to the minus gamma over m t. And that will be equal to qe over m times e to the minus gamma over m t, which implies that mass times dv dt is just equal to qe e to the minus gamma over mt. Okay? But v of t is equal to q over gamma times e times 1 minus e to the minus gamma over mt, which means that this is equal to q e over gamma minus q e over gamma times e to the minus gamma over mt, which implies that gamma vt is equal to qe minus q e to the minus gamma over mt, which in turn means that we get qe e to the minus gamma over mt is equal to qe minus gamma v of t. So mass times dv dt is equal to qe minus gamma times v. And that's what we set out to show. And so we've shown that this solution does satisfy that differential equation. All right, number 5 is kind of a long problem, so we'll take this in parts. So part A asks you to use the kinematic equations with A equals QE over m to calculate the drift velocity of electrons in a metal, assuming the mean free path lambda divided by the time between collisions tau is equal to the average velocity of an electron. So specifically show that the average velocity is equal to this expression here. Okay, so this is just kind of an alternative way to derive expressions for the drift velocity. I didn't talk about this method in class, which is why I kind of put it in a homework assignment. So let's have a look. Part A, anyhow. So this is 5, Part A. Well, so lambda, our mean free path, we're basically saying is going to be equal to 1/2 AT squared. This is just a standard kinematic equation. So this, of course, implies that tau is equal to the square root of 2 lambda over a, the acceleration. So the average velocity then is going to be equal to the distance traveled, we'll just call it d, right, divided by the time taken, tau. But this is just, the distance traveled is just 1/2 AT, so I have 1/2 a tau divided by, or tau squared divided by tau. And that means that this average velocity is 1/2 a times tau. Replacing tau with this expression we got from before, that's 1/2 a times the square root of 2 lambda over a. And I can move the a and the 2 inside of the square root, and I'll get be lambda a over 2, which is then just equal to, now we're substituting in for a, for the expression that we were given in the problem. Well, where did I put the a? QE over m. So I'm going to replace a with QE over m. And so that gives me Q lambda E over 2m. And that is the expression that we required. That's part A. All right, and part B says that since the current is proportional to the drift velocity and electric field E is proportional to the electric potential V, the result in A suggests that the current is proportional to the square root of the potential. Well, that isn't right. So assuming electrons in a metal race around like atoms in a hot gas, the ratio of mean free path lambda to time between collisions tau corresponds not to the drift velocity, but to thermal velocity. Show that with this assumption, the drift velocity becomes the expression that we gave here. And that is, we did do something similar in the lecture to that. We certainly made that assumption, but there's just a slightly different approach to it. So let's have a look at what we do here. So part B, V sub d for drift velocity, right? And that's going to be equal to 1/2 a times tau. That's equal to 1/2 a, where tau is now replaced by lambda over V thermal, which would be equal to lambda over 2 V thermal, I'm just going to put TH for thermal, times QE over M. And I think that is the result that I wanted, yes? Lambda QE over 2V. Yeah, looks good. And that's the result I was looking for. So it's pretty straightforward, that part. Okay, part C, using the formula for the current, show that the conductivity obtained with the drift velocity from this problem is half that from the lecture. Note this formula, the lecture formula is more accurate, which is probably why I used it. So part C, let's see. So from above, right, we've got the drift velocity. Let's just rewrite lambda over V thermal as tau, the relaxation time. So V sub d, I'll put the arrow up, meaning from part B, is just Q E tau, where tau is again lambda over the drift velocity, divided by 2m. And so I, the current, is going to be rho Q squared tau divided by 2m times A over L V, the potential, right, where V over L equal V over L, I did a different L, equals E. So this expression here, we'll call it sigma part B. That's what we got in part B. But sigma in class that we got was equal to rho Q squared tau over m. And so you can see that the value that we got in part B would correspond to just half of what we got in class. Okay, and the last part of this problem, part D, assume the thermal velocity of electrons to be given by V thermal equals the square root of 3 times the Boltzmann constant times the temperature in kelvins divided by the mass, where Kb is the Boltzmann constant, T is the temperature in Kelvin. Show that the resistivity of a conductor increases with temperature. Now that's something we didn't really talk about in class, which is kind of why I put it in the problem set. So let's write down here, we've got sigma, and we'll use the conductivity that we got in class instead of the conductivity we got from the problem we worked here. It's going to be rho q squared tau over m, but tau is equal to lambda over V thermal. So sigma is going to be q squared rho over m times lambda over V thermal. And we can now substitute in for V thermal this expression with the Boltzmann constant, so we'll get q squared rho lambda over m times the square root of m over 2k sub b times t. And this is equal to q squared times rho lambda over, we'll just simplify it a little bit, 2 square root of 3k sub b t times m. Okay, so rho as a function of temperature then is equal to 2 times the square root of 3 kBT m, all divided by, oops, this is outside the square root, all divided by q squared rho lambda. And so note that rho of T is proportional to the temperature, not temperature to the 1/2 in reality. So we got a result that indicated that there's a temperature dependence for the conductivity, but it does have the wrong power dependence.